Log on, tune in, find out. Another good idea from Cambridge.
All right, thank you guys very much for having me here. Yep. First of all, just to make sure that Andy doesn't stop me, my acknowledgements, I gotta thank Simon Tavares and Affymetrix and all these guys. But what we are going to talk about is about this one thing that every single one of us have, and it's called the genome. This is one of the representations that we have today, but I mean, given everyone's background, I really like thinking about the genome as just a huge program where the only codes that we are allowed to have is A, C, Gs, and Ts. Okay? The major issue here is that instead of being an R program or a C++, whatever program you guys like the most, and have like 100 lines, this thing has 3 billion letters. Okay? Different sessions of this, we could have like this tiny little region there. It could be something that would be, let's say, controlling how your body responds to a given drug. Or we could have another region like that up there, could be controlling, I don't know, the color of your eyes, right? But the amazing thing is that these chains, they are not necessarily consistent in terms of size. Okay, we could have a single one thing that would be not that. A single one thing that would be controlling, I don't know, how your body responds to things like diabetes, or another one like that blue one over there, impossible to see for you guys in the back, that would be controlling things like responses to bipolar disease, right? So this is what we've been talking, except for John, but everybody else was mentioning things about SNPs, right? And all that means is if you get two random people, what we are going to have, and we compare these genomes, what we are going to have is that the majority of the genomes will be identical, but there will be a few positions where people differ, and this is what I am particularly interested in. So back in 2008, just to give you an idea of how things were happening, we had results saying, for example, that one extra allele C on that given location would increase the chance of having type 2 diabetes by 40%, or 45% in terms of bipolar disease if you have an extra T on that one position, right? How can we assess that type of result? How can we measure whether or not we have a C, a CC, TT, CT type of thing? So Affy has this one that I call here old design, where on their array it's just a surface where we have probes, and these guys that are not tagged, these are what we call probes. These guys are 25 nucleotides long, right? Affy is well known for being this one company that has one color arrays and their probes have 25mers, all right? That's no longer true. Affy has now this new thing that they call ligation-based, and they call it axiom arrays. So for you guys who are more used to the area, you could see this as being something like what Illumina does, right? So what they have the array itself, and then what we have here is the reference genome, and then what happens is that the probe is designed so it matches the upstream up to the SNP, right? So one major difference here is that the probes no longer have the SNP that we are targeting, all right? And then what happens is we have hybridization, and then they have a hapten mix that is added afterwards, and depending on the allele, oh, come on. And depending on the allele, the scanner will capture that signal in different colors, all right? So it will be something like orange and green if you really want to follow the specs of the array. So one detail here is it is a trivial thing to do if you're looking at SNPs that are not ATs or CGs, because all you gotta do is compare the signals that you get from one channel versus the other. But then when you're looking at AT SNPs, for AT SNPs, you no longer have that nice property of having the probes being able to differentiate the alleles on the different channels. So what happens is that the probe is now designed and it actually has the proper SNP on the probe itself. Okay? The downside of this is that instead of now being able to compare two channels and just look at the ratio, for example, to make my genotype call, I have now two different probes on the same channel. Okay? That's the major difference here. It's not a direct comparison, if you may, between the channels. It really depends on the type of SNPs that you're looking at. So just comparing the two of them, what happens is our old scenario, we have 25 MERS and now versus 30 MERS, so the probes are slightly longer. SNP is not necessarily on the probe on this new platform. The SNP position for the previous ones was the 13th. And this is for me, I'm a statistician, all right? So when people come to me and they say, okay, I have this money and how many samples should I get to run this particular experiment, all right? The answer I'd love to give is, well, get the money you have, get the cost, divide one by the other. That's the ideal sample size, right? But here, and all that I want to say by that is the larger the n, the better, right? What happens, what happens here is that instead of having 4 to 6, as we are used to have, or even more depending on the version of the array you're looking at, 4 to 6 probes, what we have now 2 probes, all right? 2 single probes per allele. They are identical. They have identical sequences. Another characteristic is, well, up to a few, probably 1 year ago, a little bit more, people were used to the 1 million SNP array, the SNP6 Affy. Now it can go up to 2.5 million. It is very flexible in the sense that you can pretty much choose what SNPs you want to be there. That makes it a little bit harder for algorithm development because you have to have a genotyping algorithm that is able to account for all these different combinations that you may choose. And now the major difference is, well, we are no longer working on a single channel array, but now in 2 colors. So what do we observe? This is what you get. You scan your array and you get this picture. And what do? What we have to do is go through this image and try to identify which probes point to what allele, and then after doing some processing, being able to go to every single site that array is squaring and being able to make calls in terms of alleles. We want to know if that person is a B, or BB for 2.5 million SNPs that we may have on that platform. But we also observe things like this, right? We have, I know people who would say, well, you're going to be able to find the fingerprint of a technician there, if you may, all right? And this is something that worries us a lot right now, because this array has only 2 probes, right? So if one of your probes is there, and all we can do with 2 probes is just take the mean, things will be really, really affected, all right? This will be really bad. So what we have to do, we need to be able to identify spatial artifacts like that and remove them somehow, okay? What I'm doing currently is pretty much just ignoring every single probe that is affected by a spatial artifact like that. But what happens is if both probes are affected, then it's just bad luck. I cannot do anything. I cannot do magic here. And I just go on. So in theory, what happens in terms of image, we start with an image like that. We process identifying the spatial artifacts and then remove them out and do the downstream thing that is just calling the SNPs. Other concerns that we may have is we can see genotyping as a counting problem, okay? Most of us, actually I hope all of us, are deployed in most of the locations. What that means, I have 2 copies of alleles. I have 2 copies of alleles. So whenever, if I say that I want to count how many allele A I've got, if I have 2, then the genotype is AA. If I have 1, AB, so on and so forth. Okay? Using these characteristics, we can also use SNP arrays, for what we call copy number analysis. We want to identify regions like this where here we have a suggested deletion. But then what happens on this particular assay is that when I look at the density plots of each channel, I have that very high spike on the upper range of my dynamic range. Okay? So what that means afterwards, after I was trying to understand what was going on, and I go to the real data and read the intensities from there, what happens is that the scanner is clipping everything right there. So I'm not able to detect any change above that threshold, which suggests me that unfortunately for this particular platform, we may not be able to do copy number analysis and only genotyping. And we are done.
Okay, one very brief question.
Are these arrays